So in this video we're going to first start by talking about solubility factors. These are characteristics that influence the ability of a substance to be able to be soluble in its solvent. We've already talked about the first one with structure, how both polarity and intermolecular forces can have an impact on a substance's solubility. Pressure is another factor that can influence it. We are able to have carbonated drinks because the gas that's stored in those drinks is stored at very high pressures, which is why when you open that seal and the cap comes off, you see lots of bubbling coming out because the pressure has been dramatically decreased and the gas is no longer able to stay as soluble. Henry's law relates pressure to the concentration of the gas. The more concentrated gas you want to store, the higher the pressure is that you're going to need. So it's a direct relationship. K is just a constant for whatever solution you're working with. And P is the pressure that the solute right above the solution, which you want to be higher if you want more of that gas to be in solution. Temperature can also play a role. With solids, if you've ever made crystals, you know that higher temperatures will allow you to dissolve more of a substance. Because they're moving around more, so that there's greater amounts of space because the water molecules are in more motion, and that allows the solids to be able to interact, or whatever the substances you're dissolving it into. But you will see the amounts vary. It's not going to be just a straight graph that you might see in other cases. With gases, however, as the temperature increases, we see less of the gas being able to stay in the solution because the gas is going to be moving around more and able to escape the liquid and go out into the atmosphere. So here's a couple of examples of solubilities. The one on the left is for solids, the one on the right is for gases. And there's a couple on here where you see the solubility of the solids diminishing. And those are solids. They're still soluble, it's just not as soluble, and they're not dramatic differences. Cerium sulfate is going to be a solid that's primarily insoluble, if you think back to the KSP values that we talked about previously. But for the most part, we're seeing pretty solid increases as we increase the temperature with the amount of solid that can dissolve, and the solubility tells you when you are at equilibrium. With the gases, however, we see that things are decreasing as the temperature increases. So we're going to do one example with this involving Henry's law. We're going to look at carbon dioxide and soda. We're told that if you have it in a bottle of soda at 25 degrees, it's going to have a pressure of 4 atmospheres, but that the pressure of CO2 in the atmosphere is 3.5 times 10 to the negative 4th. So what would happen if you open the bottle versus when the bottle is closed? And again, that constant K is given to you, that 32 atmospheres per molar at 25 degrees Celsius is the Henry Law's constant for CO2. So if we take a look at this both before and after, before we would have the pressure being 4 and our constant being 32. And when we solve for the concentration of CO2 in that mixture, we would get that it's 0.13 molar. Afterwards, when we open it up and it's exposed to atmospheric pressure, the concentration is going to drop dramatically. We're going to see a concentration of 1.1 times 10 to the negative 5th. So this is a good moment to remind you, make sure you seal your bottles if you want to keep the carbonation in there, because it will go very quickly. We're also going to take a look at vapor pressures. We talked about those a little bit before, just substances in general. But sometimes when you add something and make a solution, vapor pressure will be adjusted for a solution because of that solute interfering with the ability for the solvent to escape and become a gas. We can figure out what the vapor pressure will be for the solution by calculating the mole fraction of the solvent, what percentage is really still there, and multiplying that by the original pressure of the pure solvent. So by accounting for what the pressure would be without any interference and the fraction of the solvent remaining, we can get a proportion that will tell us what the pressure of the solution would be having adjusted to the addition of a solute that does not affect the pressure because it's non-volatile and so it's going to have much lower vapor pressures than the volatile solvent. And so here's a picture to kind of help you see that. There's your pure solvent on the left, and we see that it's at a pressure of 3 atmospheres. And now that you have a non-volatile solute, the one in yellow, you see that fewer molecules are reaching the surface because they're being stopped by the non-volatile solute, and the pressure has dropped from 3 to 2. And I'm assuming that's atmospheres. So we're going to do one example with this. The vapor pressure of a solution that's got 53.6 grams of glycerin and 133.7 grams of ethanol is 113 torr. So that's the solution, not just the solvent. And we're at 40 degrees Celsius. We're going to figure out what was the pressure of the pure solvent, the ethanol, assuming that glycerin has no impact on the pressure, that it's non-volatile, and that it's non-electrolytic. And that is the truth. So with that in mind, if we have the masses of both components, we can kind of tell ethanol is going to be my solvent because it's a larger quantity. Also, that's the one we're being asked to try to find out about. And so both pressures, one involved the solution, one involved the solvent. So we need to find the mole fraction of the solvent, the ethanol, which means we need to find the moles of both components. And so to find the moles of our solvent, we're going to take the 133.7 grams of ethanol and divide it by its molar mass, and we'll get that that's 2.901 moles. We'll do the same thing with glycerin, and we'll get that it has 0.582 moles. When we solve that calculation through, we get the mole fraction of our solvent is still primarily ethanol, 0.8329. And now that we know that and the pressure of our solution, we can calculate what the pressure was of the ethanol when it was in its pure form, and it's going to be slightly higher than the solution, 136 torr. If you need to pause, I would do so now. The last thing we're going to focus on in this chapter is colligative properties. Colligative properties are characteristics like boiling point and melting point. Here it's listed freezing point, also osmotic pressure, that don't really care what's in the solution, but they care about the number of particles. So these substances are soluble and they ionize and can affect how high the boiling point would go or how low the freezing point would go, as long as there's multiple particles in solution. So the boiling point elevation formula is going to look very similar to the freezing point depression, that when you have a solute that has dissolved, it can cause the boiling point to rise because it's going to take longer for the vapor pressure of the solvent to reach the vapor pressure of the atmosphere, and that's when it would truly boil. We have a constant K, similar to what we have with Henry's law, that's equal to the difference between the temperature of the solvent in its pure form minus the temperature, the temperature of the solution minus the temperature of the pure solvent. And then that's all going to be multiplied by the molality, so that we're not involving volume with this. Since we're changing temperature, our molarity in theory would change as well as if we did not use the molality for our concentration value. Freezing point depression kind of works the same way. Again, the solute interferes with the solvent's ability to kind of form that crystal structure that you need in a solid form. And so the temperature will drop below the freezing point of the pure solvent. So a couple of examples. Here we have the freezing point of t-butanol, that's what T stands for, is 25.50 degrees Celsius. And the constant at this freezing point is 9.1 molal, or degrees Celsius per molal. T-butanol is capable of absorbing water. So if it's absorbing it, water is acting as the solute. And if you have 10 grams of t-butanol and you have a freezing point now of 24.59 degrees Celsius, how much water had to be present to cause that temperature to decrease by that amount? So we're trying to find out about the solute, and the only part of our equation that's going to help us do that is our molality. So with that in mind, we're solving for M first, which means we need to look at the difference between the two temperatures as well as our constant. Again, our temperature difference is going to be the difference from Is that just the net difference is what we're looking at. It is a drop. I'm not saying it isn't. But we really just want to know the net value since you can't really have a negative molality. We have our K constant, and then we have our M. And so that's our freezing point depression constant. When we divide both sides by the Kf, we get that our molality is 0.1 moles per kilogram. And that's 0.1 moles of water per kilogram of tert-butanol. Since we had 10 grams of tert-butanol, we should be able to figure out the moles of our water. And when we do that through, we get that we have 0.0010 moles of water in our sample. So that's our molality and our grams of tert-butanol converted to kilograms. And then we can multiply that by the molar mass of water to get the grams of water that are present in our sample. And we get that 0.018 grams of water was absorbed by the tert-butanol. If you need to pause, I would do so now. Another example we're going to take a look at is using freezing point, boiling point elevation calculations to calculate the molar mass of a solute. Here we have 2 grams of a large biomolecule. It was dissolved in 15 grams of carbon tetrachloride. So the carbon tetrachloride is our solvent. The boiling point of the solution was 77.85 degrees Celsius. We are trying to find the molar mass of the solute, the biomolecule. CCl4's boiling point constant is 5.03 degrees Celsius per molal, and the pure carbon tetrachloride boiling point is 76.50 degrees Celsius. Again, our solute is the biomolecule. Our solvent is the carbon tetrachloride. We want to find molar mass, which means we want to find grams per mole. And in order to find grams per mole, we've actually already got the grams given to us in the problem, the 2 grams of the biomolecule. So we need to use our molality to find our moles of the biomolecule, the moles of our solute. And so first we're going to solve for molal. We have our temperatures, take the difference to get our delta T. We have our constant 5.03, solving for molal like we did in the previous problem. We get that we have 0.268 moles of the solute, the biomolecule, per kilogram of the solvent. Since we had 15 grams of carbon tetrachloride, we can divide that by 1,000 to get our kilograms, 0.0150. And we can multiply that by the molality to get the moles of just the biomolecule, 0.00403. And that can now go back into our molar mass equation to get the moles of, or to get the molar mass of the biomolecule, which will be very large. Which is why we don't typically talk about biomolecules in terms of molar mass. There's another unit they use for it, and if you take biology classes, then maybe Kai and Damien can tell us about it. That they use to represent the molar mass of nucleic acids and things like that. I'm just not remembering it offhand. If you need a pause, please do so now. The last example we're going to do with this one involves anthraquinone. We're told the empirical formula of anthraquinone is C7H4O. The freezing point of camphor was lowered by 22.3 degrees Celsius, so that is the temperature change. When 1.32 grams of the anthraquinone is dissolved in 11.4 grams of camphor. So the 11.4 grams of camphor and the 1.32 grams of anthraquinone. Anthraquinone is acting as my solute. The camphor is acting as my solvent. Oops, hold on one second. We are wanting to find the molecular formula, which means we need to find the molecular mass. So we're going to solve for what we did previously, which is find the moles of the camphor, the moles of the anthraquinone. We can find the molar mass of the empirical formula using the chemical formula we were given previously, C7H4O. And that molar mass is 104.11. So using our colligative property equation, we can solve for the molality, which will give us the moles of the anthraquinone per kilogram of camphor. Since we dissolved it in 11.4 grams of camphor, we can multiply by the molar mass by the mass of camphor. I'm losing it. I'm only allowed to do videos for so long, and I'm getting close. 0.56 moles per kilogram was our molality. Multiplying that by the kilograms of camphor gives me my moles of just the anthraquinone. Now that I have the moles of my anthraquinone and I have the mass of my anthraquinone, I can find the molar mass of my molecular formula, and that will be 1.32 grams divided by 0.0064 moles, and that gives me 206.25 grams per mole. When I divide those two, I get roughly that it's doubled, so the molecular formula will be twice the empirical formula, C14H8O2. I think I'm going to have one last really short video for the very end of this chapter, which is going to deal with substances that can break apart into multiple ions.